Hello, hello. Welcome to lesson 8B. We're going to continue to talk about hypothesis tests, but in this lesson, we're going to talk about what we call error and power in a hypothesis test. All right, so let's recap what we talked about before in lesson 8A. A hypothesis test, we make our decisions, we write our conclusions based on a probability. Right? If an occurrence is really, really unlikely to happen, we say that we doubt our null hypothesis. If that probability is not too low, right, if it's not below our significance level, then we say that we don't doubt our null hypothesis. But all of that is based on a probability, which means that sometimes we can be wrong. Dun, dun, dun. So what happens if we're wrong is kind of the discussion of today. So let's look at a table where we talk about some of these errors that we could make. So here's a little table. On this side of the table, I'm going to talk about our actual hypothesis. So when we run a hypothesis test, our decision comes down to either we're going to reject our null hypothesis or we're going to fail to reject our null hypothesis. And that's, again, based on a probability. We're never 100% certain in anything that we do. So that's the decision we make based on the evidence, based on the test and the sample that we have. In real life, as in what's actually true, the null is either true or it's not true. So in two of these places, we are making the correct decision. But in two of them, we are not. So in this top left corner, right, when the null is true, but we end up rejecting the null. So we reject the null based on our evidence, based on our sample, but actually, in reality, the null hypothesis was actually true. We call this a type 1 error. So type 1 error, when we reject the null, but in actuality, the null was actually true. And the symbol we use to represent the probability of a type 1 error is alpha. And yes, this is the same symbol that we use for the level of significance because it is the same number as the level of significance. So whatever you are setting, your alpha, your level of significance, that ends up being the probability of a type 1 error. The other type of error that we can have is what we call a type 2 error. So type 2 error happens when we fail to reject the null. Right? Meaning fail to reject the null means we're kind of stuck with the null. We didn't have evidence of the alternate, so we're just saying, well, the null's not true. It's not true. We failed to reject the null, but in actuality, in real life, the null was actually false. We call that a type 2 error. And the symbol we use to represent a type 2 error is beta, which is another lovely Greek letter. Comes right after alpha. The other two places are correct decisions, right? If we reject the null and the null was false, that is a good thing. If we fail to reject the null and the null was true, that is a good thing. We made the right choice. Most of the time in a hypothesis test, one of these two green check arrows is going to happen, but occasionally we can have one of these other two types of errors. So let's go ahead and talk about this in some context. So let's consider a test for a serious disease. Like, none of us can think of a serious disease that's going on right now, surely. But in a test for a serious disease, right, we kind of have these two hypotheses. Our null hypothesis in that test is that the person is healthy. That's our initial assumption. The alternate is that that person is not healthy. Okay, always remember that your null is that kind of no effect, no change, nothing's weird, nothing's different, nothing's going on. Your alternate is that there's been some kind of change or some kind of effect. So null is everything's cool. Alternate is something happened. So those are our hypothesis tests or statements. So type 1 error, remember type 1 is we reject the null, but actually the null was true. So if we rejected the null in this situation, then that means we're saying this person is not healthy. We're rejecting the null. The person is not healthy. They have the disease, but actually the null was true, meaning the person was healthy. So we decide the person has the disease, We say we have evidence based on this sample, based on this blood sample that we took or whatever sample, that you have the disease, but actually they're healthy. Okay? And then a type or a consequence of that would be that we kind of worry them for no reason, right? We scare the person, they think they have this disease, they go in for further testing or treatment even. Maybe the treatment has a negative effect on them and everything's crazy. So that's type 1. Okay, same serious disease, but this time type 2 error. So type 2 error is when we fail to reject the null. Basically saying we don't have evidence of the alternate, so we're going to stick with the null. We can't reject it. We're failing to reject it. But in a type 2, the null was actually false. So we fail to reject the null. We think the person is healthy, but actually they're not. So we think the person is healthy, or we can't prove that they're not healthy, but in reality they do have the disease. They are not healthy. Consequence of that, all right, they don't get treatment for a disease that they have. We thought they were okay, but they actually are sick. One way to kind of really quickly remember them, and I will kind of give a caution to this, type 1 error we can think of as a false positive, and then a type 2 error we can think of as a false negative. I would caution you not to use this as the only way you remember them or keep them apart. This works really well if we're talking about like a medical test or a medical disease, because positive in that situation means like they test positive. So it kind of helps and it makes more sense. In other situations that are not like medical testing, sometimes this can throw you off. Remember, positive doesn't always mean that things are happy. It just means that we've tested that there's an effect, and that wasn't true. So it can be a little tricky, but I also love this image that's been floating around the internet for years to kind of visualize the difference. So type 1 are false positive, type 2 are false negative. There you go. All right, so let's look at another example and talk about some explanations of errors. So a potato chip producer and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer determines that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make potato chips. To make the decision, the supervisor will inspect a random sample of potatoes. So we're going to take a sample, we're going to look at the sample and decide does this sample give us evidence that more than 8% of the shipment has blemishes. All right, so in that situation, my null hypothesis, remember from last class, your null is always a statement of no change, no effect. So we would basically say P equals 0.08. In other words, right, 8% of the potatoes have blemishes or no more than 8%. In other words, the potatoes are mostly fine. Your alternate, what we think might be true or what we're testing for, right, is that if more than 8%, that's what we want evidence for. So alternate would be if P is greater than 0.08, which would mean that more than 8% of the potatoes have blemishes, so overall potatoes are sketchy. So let's talk about type 1. Type 1 error, we reject the null. So we reject the null, we say no, we think the alternate is true. So we conclude, based on our sample, that more than 8% of the potatoes in the shipment have blemishes, but in reality, the null was true, and it was 8%, maybe even less. So we decided that too many of the potatoes are blemished. We send the potato truck back, but actually the potatoes just were mostly fine. Type 2. Type 2 is when we fail to reject the null. Right? Fail to reject the null means, again, we're not necessarily saying the null is true. We're just saying we don't have evidence of the alternate. So we're kind of stuck here at the null. So that's what we're concluding. But in reality, the null was false. So we think that only 8% are blemished. Right? Potatoes are mostly okay. But in reality, the null was false. The alternate's true. There really were more than 8% blemished. A quick way to remember it, besides false positive, false negative, type 1 is when we think there's a change, we think there's an effect, but there's not. Type 2 is when we think nothing changed, but actually it did. We think there's no effect, but actually there is an effect. So then a lot of times people will ask the question, which error is worse? And if we had an answer to that question, we would obviously minimize 1 all the time. But in reality, there's not really one answer to that question. It really depends on the situation. So in our potato chip example, for the potato chip producer, for Lay's company, a type 2 error seems more serious because it may lead to lower quality chips and decreased sales. But for the supplier, right, a type 1 may seem more serious to them because it's leading to them not being able to sell their perfectly fine potatoes. So it kind of depends on the situation, and that makes it tricky. So let's go back to our little table and talk about that a little bit more. How do type 1 and type 2 relate to each other? And if we wanted to make one smaller or bigger, what would that affect? So the way that type 1 and type 2 relate to each other is kind of in a inverse relationship way. There's a lot of really interesting graphs that we can make, but I'm going to try to keep it simple on this little video. If we decide that a type 1 error is a really bad situation and we want to try to avoid it at all costs, we can make the choice to decrease the probability of a type 1 error. But what that's going to do, because remember, that's just alpha, that's our level of significance. We can do that by simply making alpha smaller. And then we end up with this. If type 1 error gets smaller, then just by default, type 2 is going to get bigger. So by decreasing the probability of a type 1 error, we are in effect going to increase the probability of a type 2 error. The same thing could be true the other way. We don't necessarily change beta ourselves, but typically if the probability of a type 2 error is smaller, right, then the probability of a type 1 error is going to be bigger. Right? So one way that we have we decide type 2 is really bad and we want to avoid that at all costs, we can make type 2 smaller simply by making type 1 bigger. Right? If we're more afraid of the effects of a type 2 error. But they do have that inverse relationship with each other. Our last little topic for this lesson is something called the power of the test. So when we talk about the power of hypothesis tests, we're very simply talking about the effect rate. How good is this test at detecting a change when there is a change? So I want you to think about a criminal trial. So let's say you are a prosecutor and you know the defendant is guilty of the crime. Like, you know. Everybody knows, you know. Right? So in our American criminal justice system, our null hypothesis is that the defendant is innocent. And then our alternate, what has to be proven, is that the defendant is guilty. So you as the prosecutor, you know the defendant is guilty. Your job is to have enough to prove that our alternate is true. Okay. So in order to do that, in order to convict the criminal, in other words, to reject the null hypothesis, what do you need? Well, you need evidence. Hopefully strong evidence. Really undoubtedly good evidence that makes it really beyond the shadow of a doubt obvious that the null is not true and that the alternate is true. Right? If we don't have good evidence, we run the risk of committing a type 2 error, right, where we fail to reject the null, but actually the null was false and the alternate was true. Right? So in a hypothesis test, the strength of our evidence is called power. Power is basically the concept that if, in fact, the alternate is true, power represents the probability that our hypothesis test will conclude the alternate to be true. Remember, in most situations in real life, we don't actually know which hypothesis is true because, again, if we knew that, we wouldn't need a hypothesis test to figure it out. Right? So we don't actually know. So power represents, if the alternate's true, it's the probability that our hypothesis test will detect that it's true. It's basically the probability that we don't commit a type 2 error. Remember, type 2, the alternate is true, but we fail to reject the null. So if we don't do that, that's power. Which means to calculate power, very simply, we can do 1 minus beta, which remember is the probability of a type 2 error. Okay. Now, typically speaking, in this intro-level stat class, you will never be asked to calculate power unless you know beta. You'll never be asked to calculate beta unless you know power. There have been situations where, as kind of on the last question of the test, the extra thinky question of the AP exam, they threw that in there. But generally speaking, it's not something that we cover, so I don't want you to worry too much about that. But just know, if you know beta, then you can figure out power, and if you know power, then you can figure out beta. In terms of our little table here, power is in that top right-hand corner, right? If the alternate is true, power represents the probability that we conclude it's true, that we reject the null and conclude that it's true. So the whole idea behind power is that if we have an alternate that we know is true, or that we're very, very confident is true, and we want to make sure that our hypothesis test proves or finds evidence that it's true, we need power to be as large as possible. We want that probability of correctly concluding the alternate is true to be as big as it can possibly be. So in that regard, there are 3 ways to increase power. The first is to increase alpha. Remember, alpha is your level of significance. And if your level of significance goes up, right, that means type 1 error goes up. But remember, if type 1 error goes up, then type 2 error goes down. And since power is 1 minus type 2, then power will then go up. So it's a kind of a cause and effect chain reaction there. Right? Increasing alpha will increase or lower type 2, thus increasing power. But remember, the downside of that is that we are in effect increasing type 1, which may not be ideal if we're not 100% sure, right, about our alternate being true. So that's all a little bit of a downside. The second thing that we can do is increase sample size. Right? Increasing sample size, generally speaking, is always going to make us a lot more confident and a lot more sure in our conclusions. So that obviously is going to decrease both of our types of error, which would then increase power. In terms of the graphs, right, power exists in the very tail ends of our normal model graphs. So increasing sample size will make the graphs less wide. We'll make them a lot narrower, which will make those little tail areas a lot smaller. Right, so a narrower sampling distribution would end up being a lower type 2 error, which would then increase power. Again, there's great visuals for this. I'm going to give you a suggestion of a video to watch if you want more visuals for all of this. Downside of that second option is that taking a bigger sample size is not always possible and realistic. Like in real life, taking a bigger sample size costs money, costs time, effort, things that we don't always have. So yeah, it's a great solution, but is that feasible is the question. The last thing is probably the most conceptually weird thing to understand. Is to increase what we call the effect size. Effect size is basically the difference between the null hypothesis and the alternate hypothesis in terms of what actually is true and what our null hypothesis is. So if what is actually true is really far away from our null hypothesis number, then we have a really big effect size. If what is true is really close to our null hypothesis number, then we have a really small effect size. So in effect, what's happening with this third one is we're really just saying, make the new thing, make our alternate hypothesis really, really, truly better, by a lot. So if we're trying to show this new medicine works way better than the old one was only 8% effective, but this new one is so much better. Well, it's going to be a lot easier for our hypothesis test to show that it's true, that it's better than 8%, if it's 12% versus if it's 9%. So if we're saying it's better, we want it to be a whole lot extra better, because then it'll be easier to prove that it's better, right? Increasing effect size kind of moves apart those normal distributions and makes type 1 and type 2 lower, which then in turn increases power. All right. So as a last little step, the downside of that one is it's not really something that statisticians have control over. That would be more on the side of the testers or the people who are kind of creating the products or whatever we're dealing with. Okay. So I'm going to put this link somewhere in this video, but this is a crash course video that explores the topics of error and power and how to increase power. It has a lot of really good visuals that they spend money on making, and it's easier for them to do than it is for me to do. So if you want some more visuals or some more explanation of all of this stuff, I would definitely recommend. It's a great video just to explain all of these concepts a little bit more. It's about 12 minutes long, but even the first like half or so of it gets into a lot of the good topics that you really need to know about. So definitely suggest that one. And that is it for today.